So this is the 2016 chemical equilibrium question. So let's have a look at the question overall. It's actually quite an easy question this year, I think. Initially it asks about stating and using Le Chatelier's principle, which should be pretty straightforward if you've studied Le Chatelier. Then it's asking to state the effect of catalyst on equilibrium, which of course there is no effect on equilibrium. And then there's some calculations about calculating equilibrium concentrations and the equilibrium constant. But this is quite an easy version of this. The hard work really is in working out concentrations based on the mass given. Once you've done that, it's quite straightforward. So, obviously Le Chatelier is core to this topic, so you should be able to answer these types of questions looking at the effect of temperature, pressure, change in concentration on the position of equilibrium. So let's start off answering Le Chatelier's principle itself. States that systems at equilibrium move to oppose any disturbance. When a system is at equilibrium, it's in a low energy state, a low energy environment. So therefore, if we try and move it from that environment, it's going to do anything it can to get back to that position. So the system will move to oppose any disturbance, such as change in temperature, concentration, or pressure. And then it asks about how do we maximize the yield of this reaction, knowing what we know about equilibria. So we see here in our thermochemical equation that we're given, we're told that delta H is negative. So that means that this is an exothermic reaction. This reaction gives off heat as it proceeds. So if we want to increase the yield, we would reduce the temperature, because by reducing the temperature we are disturbing this equilibrium, and Le Chatelier says the equilibrium will shift so as to try and change this disturbance. So if we reduce the temperature, the reaction will shift towards products, because that increases the heat produced, so therefore will increase the temperature. So to improve the yield of an exothermic reaction, you decrease the temperature, and this will shift to the side, the reaction to the product side, to produce more heat. What about pressure? Well, if we look at the number of gas moles on the reactant side is 3, and on the product side is 2. So Le Chatelier says that the system will move to the fewest number of side with the fewest number of gas molecules if we increase the pressure, because it will try and reduce the number of molecules in the environment and therefore reduce the pressure. So increasing the pressure will shift the equilibrium to the product side. So the answer here is to increase the yield, we would reduce the temperature and increase the pressure. Finally, it asks us why would we not use these temperature conditions industrially? Well, the clue is in the question. We see in the question that we're told that a catalyst is used. So if a catalyst is used, this must be a pretty, this reaction rate must be pretty slow. We must have to include a catalyst to improve the rate of reaction. So generally, if we decrease the temperature, we are going to decrease the rate of reaction further. So therefore, we will decrease the rate of reaction so much that it becomes too slow to be industrially viable. So we don't use our equilibrium knowledge in this reaction industrially, because the rate of reaction will be too slow. Okay, the second question, part B, is kind of a trick question really. The effect of catalyst on equilibrium. The equilibrium is not affected by catalyst. All a catalyst does is increase the rate of reactions, both the forward reaction and the reverse reaction. So we achieve equilibrium faster, but it doesn't improve the yield of reaction. It doesn't improve the overall yield of reaction. It doesn't change the equilibrium in any way. So the effect of catalyst on equilibrium has no effect on equilibrium. We still have the same ratio of reactants and products, and therefore the same value of Kc, the equilibrium constant. But it does speed up the rate of both reactions, forward and reverse, so that equilibrium is reached more quickly. The word reverse here is missing from this text. Alright, so now some calculations. So we're given some detail about the reaction environment that was set up to produce some sulfur trioxide. So we're told how much sulfur dioxide and how much oxygen were added to this vessel and asked to work out what the equilibrium constant is. So to work that out, we first need to write the equilibrium constant expression generally. So the equilibrium constant will be the concentration of products divided by the concentration of reactants, accounting for the number of moles of each. So we have concentration of products, there are 2 moles of it, so it's SO3 squared, divided by the concentration of reactants, SO2 squared, times the concentration of oxygen. So we have SO2 squared multiplied by oxygen. An easy 6 marks. Now we want to use this equilibrium expression, but to use this equilibrium expression we need to know the equilibrium concentrations. So to work out the equilibrium concentrations, it's the easiest thing to do is make out an ICE table. Put in the concentrations we know, and then work out the equilibrium concentrations. So here we are given masses, so to change mass to concentration we first need to change mass to moles, so moles is mass divided by molar mass. And then we're told that this is in a 50 litre flask, so we'll be able to work out the molarity by dividing that number of moles by 50, so molarity being the concentration. So let's look at some examples. We had 96 grams of sulfur dioxide, so the molar mass of sulfur dioxide is 64, so that means we have 1.5 moles of sulfur dioxide in a volume of 50 litres, giving us 0.03 molar. We had 24 grams of oxygen. The molar mass of oxygen is 32, so therefore we have 0.75 moles of oxygen in a volume of 50 litres, giving us 0.015 molar. Before this reaction started, we had no product, so therefore its concentration is 0. So we know the initial concentrations. In this question then we're told at equilibrium we have this amount of product. So we can work out the number of moles and hence the concentration of product by working out the number of moles, 112 divided by the molar mass, gives us 1.4 moles in a total volume of 50 litres. So now we know the concentration of our product at equilibrium. We know one of the terms in our equilibrium expression. What are the other two? Well, we can work out the other two by looking at how much this changed. To go from 0 to 0.028, sulfur trioxide increased by 0.028 molar. If 2 moles in this reaction increase by 0.082 molar, well then 2 moles of reactant must have decreased by 0.028 molar. So the equilibrium concentration of the sulfur dioxide can be calculated. Similarly, if 2 moles decrease by 0.028, well then 1 mole decreased by 0.014. So this means then our equilibrium concentration will be 0.03 minus 0.028 for sulfur dioxide, for oxygen 0.015 minus 0.014. So now we know our 3 equilibrium concentrations. We can plug these values into our expression for Kc, being careful with using the calculator and dividing by values of squares, and this gives us this value, 196,000